Hello students, welcome to today's session. The topic of today's session is finite automata and its tips. We are going to gain knowledge about finite automata and the two types of finite automata, which includes non-deterministic finite automata and deterministic finite automata. Let us enter into the session.
A quick note before we get started. I will use the term machine and automaton interchangeably. They do mean the same thing, and the plural of automaton is automata. A finite state machine, also known as a finite automaton, is the simplest computational model we can construct. It has extremely limited memory, but it can still do many things, and these machines are actually very often used in our everyday devices. For example, the controller for switching an oven on or off is a finite state machine. This controller will have two states, on and off. Let's say this oven is brand new, so it first starts in the off state. Whichever state we start in is called the start state, and we have a little arrow pointing at it. Now, when the button controlling the controller is pressed, it goes into the on state, and if the button is pressed again, it goes back into the off state. Pretty simple, right? So let's build on that understanding and construct a slightly more exciting machine. Let's construct a machine that takes in a string of weather data as input and tells us whether a heat wave occurred in a given year. In India, the India Meteorological Department considers it a heat wave if the maximum temperatures reach 45 degrees Celsius for 2 consecutive days. So using this definition of a heat wave, let's construct our machine. Let's say this is our start state, and we're just going to call it Q0. If we hit a day where the temperature is over 45 degrees, we transition into this new state, which we will call Q1. And if we hit another day where the temperature is over 45 degrees, we transition into this other state, which we will call Q2. Since a heat wave is defined as having 2 consecutive days with temperatures over 45 degrees, then when we reach Q2, we know that a heat wave had indeed occurred. So we call Q2 an accept state, and to represent the accept state, we draw another circle around Q2. And now to complete our machine, going back to our start state Q0, if the temperature is not over 45 degrees, we will remain in the same state. And if we are in state Q1 and the next temperature read drops below 45 degrees, then we will go back to our start state Q0, because for it to be considered a heat wave, temperatures must be over 45 degrees for 2 days in a row. And if we are already in our accept state Q2, we don't have to go anywhere because a heat wave has already occurred. And finally, we'll just modify our machine a little bit more, and let's use a 1 to represent a day with a temperature over 45 degrees, and we use 0 to represent a day with a temperature less than 45 degrees. And there we have it. Our finite automaton, which we will now call M, will tell us if a heat wave had occurred. Notice that the automaton will enter the accept state if it takes in any string containing 2 consecutive ones as input. All these strings that eventually arrive at one of the machine's accept states are a part of the language of the machine. So the language of this machine is a set of all strings containing 2 consecutive ones. We say that the automaton recognizes this language, and it accepts all the strings in the language and rejects those that are not in the language. So M accepts 11, 110, 0110, and so on. This kind of automaton is called a deterministic finite automaton, or DFA for short. They are called deterministic because for every symbol of an input string read, we will always know what the next state will be. The next state is determined. What we have here is a state diagram of the DFA, and to formally define DFAs, we use a 5-tuple. Q is a finite set of the machine states, and for our machine M, that would be the set containing Q0, Q1, and Q2. Sigma is a finite set called the alphabet, which are the kinds of symbols that are recognized by the machine. So in this case, it is the set containing 1 and 0. Delta is the transition function, which tells us where states transition to given an input symbol. For example, Q0 transitions to state Q1 when it reads a 1 and remains in Q0 when it reads a 0. Q1 transitions to Q2 on a 1 and back to Q1 on a 0, and when we reach Q2, we will always remain in Q2. Q0 is the start state, and finally, F is a set of accept states, also known as final states sometimes, which in this case would just be the set containing Q2. One final note on finite automata: a language is also a regular language if it is recognized by some finite automaton. So the language containing all the strings with 2 consecutive ones is a regular language, since we had constructed an automaton that recognizes it. Now that was quite a bit of information, so let's just summarize what was said in this video. 1. DFAs are 5 tuples that can be represented with state diagrams. 2. If the last symbol of an input string causes the machine to be in an accept state, then the machine accepts the string. 3. The language of a machine is a set of all strings it accepts. And finally, a language recognized by some finite automaton is called a regular language. I will now leave you with all this to digest, and a very gentle reminder that as you may start constructing DFAs, designing automata is a creative process that takes time and practice, the same way it does to design any other work of art. Recall how a deterministic finite automaton takes in a string as an input, and for every symbol in the input, we always know which state to transition to next. Another kind of finite automaton is called the non-deterministic finite automaton, or NFA for short. It is called non-deterministic because, unlike DFAs, for every symbol in the input, the next state to transition into is not always determined. There can be 0 or more than one state that a machine could choose to transition into. For example, this is a DFA, which we will call M, that accepts any string that contains a 1 in the third position from the end. So it accepts 1, 1, 1, and it also accepts 1, 1, 0, 0, but it rejects 1, 0, 0, 0 and 1, 0, 1, 1. The NFA that recognizes the same language will be as simple as this. Notice how when a 1 is encountered, Q0 can choose to remain in Q0, or it could transition into Q1. There are also no arrows coming out of the accept state Q3. However, like the DFA, it still accepts 1, 1, 1, and it also accepts 1, 1, 0, 0. You might have noticed how it also could have rejected 1, 1, 1 and 1, 1, 0, 0 by choosing to remain in Q0 the entire time. And you aren't wrong. However, the NFA accepts a string as long as there is at least one path to an accept state. So although there is a path that would reject the string, the NFA still accepts the string because there is another path to an accept state. Let's look at another example to better understand how an NFA accepts the string. Consider this NFA. By construction, this NFA would accept any string that ends with a 0 and will never accept the string that ends with a 1. So on an example input 1, 0, 0, it could take this path or this path and accept the string, or it could take this path and reject the string. However, it doesn't matter which path the NFA decides to take. As long as there exists one path that causes the machine to end in an accept state, then we say the NFA accepts the string. Additionally, NFAs can also transition on the empty string. When an NFA chooses to transition on the empty string, no symbol from the input string is consumed. So going back to our first NFA that accepts all strings containing a 1 in the third final position, let's add these two new states with an empty transition. The NFA now accepts all strings containing a 1 in the third final position, or it also accepts the single 1. What we have been looking at is a state diagram of an NFA. And like DFAs, NFAs are also 5 tuples when formally defined. Q is the finite set of the machine states. So for our previous NFA, that would be the set containing Q0, Q1, Q2, Q3, Q4, and Q5. Sigma is a finite set called the alphabet, which is all the symbols recognized by the automaton. So in this case, it is the set containing 1 and 0. Delta is the transition function, and because NFAs can transition on the empty string, this symbol here represents everything recognized by the NFA along with the empty string. And because NFAs can have 0 or several choices to transition into, the transition function gives us a set of possible states instead of just a single state. And that's what this P of Q symbol here represents. So going back to our NFA, the transition function is defined like so. Q0 will remain in Q0 on a 0, and on a 1, it can choose to remain in Q0 or transition into Q1, or it could empty hop over to Q4. Q1 can only transition into Q2 on a 0 and 1. Q2 can also only transition into Q3 on a 0 and 1, and Q4 transitions into Q5 on a 1. Finally, for the states and symbols that have no transitions, the transition function will just result in the empty set. Q0 is the start state, and finally, F is a set of accept states, also known as final states, which in this case is the set containing Q3 and Q5. You might have noticed that this seems very similar to DFAs. And you might have also noticed that a DFA could probably pass as an NFA too. In fact, like DFAs, a language recognized by an NFA is also a regular language. This means that any language that a DFA recognizes can be recognized by an NFA too. And for any language recognized by an NFA, we can always construct a DFA that recognizes the same language. Isn't that a little surprising? Especially after seeing how different the two are constructed. But are NFAs more powerful than DFAs in any way? Not at all. Non-determinism only allows us to construct machines more simply. NFAs can only do as much as DFAs can. So, let's summarize everything that was said in this video. 1. NFAs are 5 tuples. 2. Unlike DFAs, an NFA can also transition on the empty string. 3. Unlike DFAs again, the transition function produces a set of possible states instead of a single state. And finally, languages recognized by an NFA are also regular languages.
Let me summarize what we have seen in today's session. In today's session we have gained a knowledge about the finite automata and the 2 types of finite automata, which includes the deterministic and non-J-deterministic finite automata. We also have gained insights into the regular languages which recognizes the finite automata. Thank you all.